Hi! In today's video, we're going to be talking about elimination mechanisms. So there are two major types that we're going to discuss. And first, we're going to start with a common intermediate that we actually saw from our substitution reactions. So if you have this alkyl halide, one that can readily eliminate and give you this stabilized tertiary carbocation, you can form an intermediate that's going to be involved in the first type of elimination mechanism we're talking about. So in this case, we're going from A, the starting materials, to this much higher energy product, this carbocation B, and now we have our water molecule around. Now in the substitution reaction, the water molecule acts as a nucleophile, but water can also act as a base in this scenario and abstract this proton that is alpha to the carbocation. So if it does that, you end up observing an elimination reaction occur. And so you form this new product, C. So we call this an E1 mechanism. So this is, again, it's an elimination, that's why you have the E there, and the 1 because it's unimolecular, meaning that the rate determining step the only thing that's important in the rate determining step is this loss of the bromide to form the carbocation. Everything else occurs after the rate determining step. So what happens if there are multiple alkenes that are possible? So in the previous example, there's only one alkene possible. But what happens if there are multiple alkenes possible? Let's look at that. So again, in this case, we can lose the bromide and form this secondary carbocation. It's not as stable as tertiary, but it's still possible. And if that occurs, now you have several different protons that can be abstracted to give you different outcomes of alkenes. So if we follow down and abstract one of these terminal protons from this methylene, you can observe this terminal alkene, highlighted in blue here. If you abstract one of these purple protons, you can get this alkene here, but if you abstract the other one of those purple protons, you can observe this alkene being formed here. So these types of alkenes are actually closely related. They have an orientation. One is called trans, that's a new word for us, meaning on the opposite side, and cis, a cis alkene, meaning on the same side. In the context of alkene nomenclature, we also have another word we can use, or another letters that we can use. We use the letter E, and that stands for Entgegen. It's a German word. If I pronounced it incorrectly, I apologize. And the cis form is called the Z stereoisomer for Zusammen. The way I like to remember Z, it's kind of silly, but I like to remember Z is the same side. So you have to kind of say that with perhaps a French, Italian weird accent to yourself. In any case, so cis is Z, or the same side. So that means that the substituents on that with the highest priorities are on the same side of the alkene. So a trans alkene, or in this case the E, is the most stable, or it's the major product, and that is a steric argument when you're comparing the trans versus the cis. The least stable product in this case is the least substituted alkene, and that's a principle that is often referred to as the Zaitsev principle, and you'll hear me talk about that in class as well. So let's look at a scenario. So we looked at the scenario where there's a intermediate and then there are two transition states and one intermediate. Let's look at the single transition state version. So in this case, we have a strong base in the form of T-butoxide, and we have bromoethane. So the T-butoxide can abstract this proton and in the same step kick off the bromide as a good leaving group. This gives you ethylene as your product. So if we're looking at an energy diagram, you see you're going from your starting materials to products and only going over one transition state. Let's look at the nature of that transition state. So all of these atoms have to be aligned, and so you are forming an oxygen to hydrogen bond at the same time as you're breaking a hydrogen to carbon bond. There's a double bond forming, and your carbon to bromide or leaving group bond is breaking. So all of these bonds are being broken and made simultaneously. So let's now look at what we call this. We call it an elimination reaction, an E reaction, and 2, because there are two molecules that are involved in this rate determining step. So let's look at the orbital requirements that are, the orbital alignment that's required for this transition to occur. And so first we can look at this carbon-hydrogen bond that we're breaking. And so the arrow is showing us that we are taking the electrons from this bond and putting it into a double bond. So we can show the CH sigma bond here. Now if we look at the carbon-halogen bond that's being broken, we are putting electrons into something. Well, what are we putting the electrons into? We're putting the electrons into the carbon-halogen antibonding orbital. And as it turns out, these are nicely aligned if they are on opposite sides of the molecule. So as you take these electrons and put them into this antibonding orbital, you form a new type of bonding orbital, this pi bond, this double bond, which is highlighted in red here. So if you were to keep track of the other hydrogen atoms that are on this molecule, you can see that these two are up and these two are down. And as you are moving this molecule from the transition state toward the product, these two will go down at the same time as these two will move up. And the final product, all these atoms are coplanar, so they're all on the same piece of paper. If you were to highlight one of these locations with a red ball and one of them with a blue ball, you'll see that the orientation that they start is how they finish. So in this case, the red ball and the blue ball are on opposite faces of this page, and they wind up on opposite sides of this alkene. So we can now say that this is a trans alkene that's being formed. So this orientation is called anti-periplanar, and it's a really important orientation for us to think about. And we can look at this as a Newman projection. So if we look down this bond, we can see that the red ball and the blue ball are on opposite faces of this molecule, and this leaving group and this proton that's being abstracted are anti-periplanar, and this is the orientation where the orbitals are best aligned. So when we look at these in ring systems, they are locked. So unlike a conformational analysis where with a single bond where you're able to rotate, you can't rotate any of these bonds. So let's look at the outcomes of a deprotonation of this versus this, these two cyclic products. So in the case of the first molecule, there are two protons that are anti-periplanar to this leaving group, to this bromide. If you abstract this one on the top, you're going to wind up with a more substituted alkene. If you abstract this one at the bottom, you're going to wind up with a lesser substituted alkene. So the major product, your Zaitsev product, is this more substituted. You'd still form some of this, but again, the major product, which I often ask for, is this one to the left. Now in this scenario, there are no hydrogen atoms that are anti-periplanar at this topmost position, and so there's no deprotonation that's possible. You're only going to observe the less stable or the anti-Zaitsev product. And again, that's because there's this stereochemical requirement. We often call it a stereoelectronic requirement. Let's look at this finally with a chair. Organic chemists love our chair structures, and let's look at this molecule where you have a chair structure where you have a cyclohexane. So when you see a cyclohexane, you should be thinking, I better draw this as a chair. So let's go ahead and draw this as a chair. So if we draw the most stable chair structure, we will see one particular conformation. And let's go ahead and draw the ring flip of this to look at the other conformation as well, because oftentimes you have to look at both. The next thing we're going to look for are where are the anti-periplanar hydrogen atoms, or where are the anti-periplanar bonds. So in this first molecule, you see that the anti-periplanar bonds are actually carbon-carbon bonds. So those aren't bonds that we can remove with a base. So this structure is not going to be reactive in the E2 mechanism. This structure, on the other hand, you have a methyl that is anti-periplanar, so there's a carbon-carbon bond. That's not going to be removed. But you do have this hydrogen atom, this carbon-hydrogen bond that can be abstracted with a base. And sure enough, a base is going to come along and abstract that hydrogen and give you this anti-Zaitsev product, again, similar to the previous example. And so if we were to color code the rest of these atoms to give us a frame of reference, you could recognize that if you had one of these two hydrogens differentiated from the other one, you'd know that this one that's highlighted in blue is now found in the product. Similarly, let's highlight some of these other hydrogen atoms that are on this molecule so we can keep track of this molecule. So again, models are a great way of looking at this, and being able to draw your chair structures is really important in the understanding of elimination reactions with chairs. Thank you for your time, and I look forward to seeing you next video.